Hello, and welcome to this podcast on vectors and scalars. Now, vectors and scalars is a relatively small bit of content which is at the end of a measurement and uncertainties unit in the IBDP physics, but it's not one that you would normally study alone, or at least maybe just briefly as an introduction before you really started using it in other topics. It's pretty much unavoidable when discussing vectors. If you actually want to give any examples, you have to give examples from other topics. Fortunately, the first non-introductory topic, that of mechanics, is generally, not always, but is generally the second topic that is taught, and certainly will involve vectors. So you will get a chance to use these fairly shortly. In terms of the information from the IB, from the subject guide, then it just says, vectors and scalars, which is kind of the title there, and then dealing with vectors, combination and resolution of vectors, either putting vectors together or splitting them apart, and solving problems involving vectors using graphics and or algebra. And the data book equations, or data book equation and diagram, which we will come to shortly. So, what's the difference between a scalar quantity and a vector quantity? Well, both of them are descriptions of quantities, in other words, things that you measure, and that's what ties it in with the rest of this unit, because we're still dealing with measurements. Scalar measurements, scalar quantities, are ones that have a size, they have a magnitude, they need a number to describe them, but they do not have a direction. And there are many, many, many examples, and we'll see some more later, but for now, 3 examples are speed. So the speedometer in a car or other vehicle registers how fast you're traveling, and it doesn't care about the direction. Okay, it's irrelevant. Similarly, time doesn't really have a direction. Yes, you can say backwards in time and forwards in time, but when you're measuring, you're really just talking about a number. You don't have to specify a physical direction. And similarly with temperature. Although temperature in many scales might have negative values, that doesn't again indicate a direction, it's just a number. And Kelvin, as a temperature unit, the SI unit, doesn't even have negative numbers. The contrast is with a vector. So a vector is a quantity which again does have magnitude or size, it needs a number and a unit, but it also does have direction. And unlike in scalar quantities, if you're adding or subtracting vectors, then you do need to use a vector version of algebra, not just linear algebra. So one example that we will be looking at further in topic 2 is force, but you've probably encountered it at least initially somewhere before. And so the idea that force is something that can be bigger or smaller or stronger or weaker, it has a magnitude, it has a number, but it also very clearly has a direction component as well. You'll see that I've drawn force there using an arrow. Come back to that in a minute. So here is just a more complete list of scalar quantities and vector quantities, and inside the brackets I've put some of the symbols that may be used for those quantities. Note that those are symbols for quantities, not symbols for the units that we associate with those quantities. So as I said, we can represent vectors using arrows and label those arrows. Notice that throughout my own presentations, generally I will just label using ordinary text font. However, in some textbooks, in some teachers, you might find that they are particularly using bold font, or they draw an arrow over the font, the letter, in order to indicate that they are referring to a vector quantity rather than a scalar quantity. When you're drawing arrows, arrows have 2 relevant components. They have a direction. The direction of the arrow shows the direction of a vector, and they have length, with the length showing the magnitude of a vector. Note that, of course, in our 3-dimensional or 3 dimensions of space universe, these arrows should be able to indicate direction in any of the X, Y, or Z axes, but throughout most, at least, of the DP physics course, we'll be worrying mostly about 2-dimensional, or if we do 3 dimensions, we'll use special symbology to represent directions in and out of the paper, in and out of a page or the screen. So what's this vector algebra we were referring to earlier? Well, sometimes you need to combine vectors, and this is something that you will see later. If we want to work out the overall force on an object, we combine in a vectorial manner all of the forces acting on an object. There are two ways of doing this. One way is graphical. Okay, so you take one vector, generally it doesn't matter which one, and you add the second vector onto the end of it. You draw another line, an arrow between your start point and your end point, and that line is the addition of the two vectors. Okay, if you want to do this properly and actually get measurements out of it, then you need to get serious with rulers and protractors and pencils, sharp pencils, which is not normally worth the bother if a calculator is closer at hand. However, it is sometimes worth quickly sketching as accurately as you can without getting to the level of being super accurate and taking a long time about it. It is useful sometimes to sketch what these vectors will look like, because then you have an idea what the answer will be before you calculate it drawing with a protractor and using the algebraic methods. So adding vectors graphically is not something you would do seriously in order to get the answer, at least not most of the time, but it is something that you might do quickly in order to give you an indication of what the answer might be as a sort of checking or pre-checking mechanism. If we have two right angle vectors and we try to add them, so we have A here and B, then it's not that challenging. We can do this using algebra quite easily. We take one and draw it on the end of the other, as I have just done there, and then you have a resultant. That's kind of the graphical part of it, but we can use mathematics to work out what the length or magnitude of that arrow will be, magnitude of the force, and what the angle, or the angle at least from the horizontal, will be. Okay, so we can use Pythagoras to work out the magnitude. It will be c squared equals a squared plus b squared, so a and b take the square root of those squareds and you will find the magnitude, and the angle is used using basic trigonometry. Resolving vectors is kind of doing it the other way around. You take a vector, any vector you like, and you split it into two vectors, one of which is oriented horizontally and one of which is oriented vertically. And if this is the angle, then you would use f sine theta or f cos theta or whatever the magnitude is, sine theta or cos theta, in order to do the resolution. The data booklet has a quick diagram, as we saw, which is a quick reminder of which is which. But as a fallback, or as a first option, generally, if it's drawn at 45 degrees or the equivalent radians, then obviously both the sides will be equal. If it's not drawn at 45 degrees, then one side will be longer than the other. And if you have a good diagram or mental picture of what's going on, you'll know which is the longest one. And if you simply take your calculator and put f sine theta and f cos theta and compare the output, it's often easy to see which is the one that you need. And you often need the other one anyway, so hey, you might as well do the calculation for both. Okay, so if you want to add two vectors, then you need to take those two vectors and resolve both of them into their horizontal and vertical components. So here we've done that. We've taken vector 1 and vector 2 and we've split them into two components representing vector 1 and two components representing vector 2. And the whole point is that these components are in the horizontal or vertical plane, which makes it very easy to add them. So you can add the two components to get one set of right-angled forces, and we've just seen how you can combine those back to a single vector. So combine them to a single vector, and again you can use trigonometrical techniques in order to determine both the magnitude, the length of the arrow using Pythagoras, and the angle using basic trigonometry. So that was adding. Subtracting works pretty much the same, because subtraction is just the same as addition. All you have to do is remember that the arrow on one of your forces points in the other direction. Okay, but other than that, it's just the same thing. Resolve the vectors and combine. Okay, thank you very much for your attention.